Okay, we're back, and so now this is going to be a comparison of what you already know with what we're going to be learning today. So on the left-hand side is everything dealing with electrostatics, which is going to be charges which are not moving. And we found that they were caused by electric charge. So the cause of electrostatics is going to be electric charges. Okay, then we had a definition of conservation of electric charge, and then we were able to draw a region of space created by that charge, and we called that the electric field. So we want to see if there are analogous concepts when the charge is moving. So I want to point out that even if the charge is moving, it is going to have an electric field, and it is going to be subject to an electric force. So everything that we've talked about for electrostatics is true if the charge is moving. But in addition to those concepts, we're going to add additional concepts for moving electrical charges. Okay, so what is the cause of magnetism? It is going to be moving electric charges. So whenever an electric charge moves, it's going to create a magnetic field around it. What do you think conservation of magnetic charge would be? So conservation of electric charge meant that you can't create or destroy electrical charges. So conservation of magnetic charge would mean that you can't create or destroy magnetic charges. So what this means is that if you've got a magnet, and a magnet has two poles, it's got a north pole and it's got a south pole. Okay, now if you broke that magnet in two, do you think that you could have the north pole on one side and then the south pole on the other side? Well, yeah, you do. But it also will create a new pole so that both magnets now will have a north pole and a south pole, so that you cannot isolate individual magnetic poles. So they're called magnetic monopoles. That's what you would get if you took a magnet and you broke it in half and you isolated the north pole on one side and the south pole on the other. It doesn't happen. Although, according to some theoretical physicists, magnetic monopoles should exist. And we're not even going to get into that. All right, so for our purposes, we're going to say that when you break a magnet in two, you always end up with two new magnets. Okay, now what would be the magnetic field? So it's worthwhile going back to that picture over there, and we said that if you had let's say it was a negative charge Q, and then you took a positive, a teeny tiny little positive charge, and you let go of it, it would be attracted to the negative charge, and then it would make what we referred to as the electric field, and that was given by E. So what we would like to know is if you take an electric charge and you move it, would it create a region of space surrounding it? And it does. We're going to call this the magnetic field. And so we're going to start with the magnetic field of a current carrying wire. So here is our wire. It's going to carry a positive current. So this is a positive current that is going to be going in this direction. Now you can have a negative current, and a negative current would be going in the opposite direction, and then that's what the electrons would do. So now this is where it gets kind of confusing. Electricians like to think of the things that are making the current in a wire as being negative electrons, which they are true. But physics people like to always use positive charges whenever they do their calculations. So you notice that this was a positive charge up here that was used in order to get the electric field. So similarly, they like to think of currents as being the flow of positive charges. So just remember that this is a positive current, but what's really happening is it's being created by a negative current, which is going in the opposite direction. So I hope that that's not too confusing. But physics people like to use positive currents, and they like to use positive electrical charges. So what would the magnetic field of a current carrying wire be? And so in order to do this, you need to use your right hand, and this is going to be called the right hand rule. Your thumb is going to point in the direction of the current, and then your fingers are going to curl around the wire. So in this case here, my thumb is pointing in this direction, so I would need to have my magnetic field is going to be circling around that wire like this, and it's going to make circles. So you're going to have a circle, and inside of a circle, inside of a circle, inside of a circle. So you have a whole series of loops that are located within each other. They don't cross. So these lines, these circles, they do not touch each other. And the further away you get, the weaker the magnetic field is going to get. The further away you get from the electric charge, the weaker the electric field is going to get. Now, you also have another set of circles. So over here, you would have an identical set of circles that would go around the wire. And then there would be another circle that would go around it, and another circle that would go around it. So it's an infinite number of circles that are next to each other, and then each circle has another circle that is surrounding it. And that's a representation of the magnetic field. So this time we're going to abbreviate the magnetic field with the cursive B. So now you might be saying, well, why not just use the letter M? Well, don't ask me. So it's scientists. So if you invent this stuff, then you get to call it anything that you want. And so this is the magnetic field B, and then this is the electric field E. The official metric unit for magnetism is going to be called the Tesla, named after a scientist. So again, it's a capitalized unit, the Tesla. All right, now that we know what the magnetic field of a straight wire is, what do you think it would look like if you took that straight wire and you bent it into a circle? So here, for example, is a circle of current. Okay, so I'm going to hold it like this, and it's very hard to see the opposite side of it here, the way that I'm holding it. Okay, so let me illustrate this with a circle, and remember that the circle ought to be actually edge on to you, and we know that it's going to have circles around it, so that if on the edges, so let's look on the edge here, you would have a circle that would be going around it, and I'm going to make my magnetic field doing that, and then the same thing is going to be true on this side over here, but it needs to be going in the opposite direction. So on this side, it's going to be doing this. So you can verify that with a piece of string and then making a circle around it, and then just prove to yourself that that would be true. And then this thing would, again, have another circle around it, and then this thing would have another circle around it, and so forth. But you'd also have circles here, and you'd have circles over here, but you can't see them. Because let's look at this circle that is right there. You're looking at it edge on. So you're trying to look at a circle that's right here, but you're trying to look at it like this. Now, if you were able to turn the circle, you'd be able to see it, okay? But you're looking at it edge on. So we're not going to be worried about these circles here and then these circles over here because they're very difficult to see. Okay, now let's compare this picture to a bar magnet. Okay, so if you have a bar magnet, so a bar magnet is going to have a, let me put it up here. So if you have a bar magnet, it's going to have a north pole, and then it's going to have a south pole. All right, now we want to draw the magnetic field of a bar magnet. Now, there's a couple of different ways that we can do it, but the way that scientists do is they pretend that they have a teeny tiny little north pole. Now, do you remember that I just got through saying that you can't isolate a north pole from the south pole? But that doesn't stop theoretical physicists. So they pretend that they have a teeny tiny north pole and they want to know what would happen to it. So in the same way they use a positive test charge, they use a north pole in order to test for magnetism. So what do you think happens when a north pole interacts with the north pole? You can try it with a compass or with the magnet. It repels, so that the magnetic field is going to be coming out like this. If you took your north pole and you put it here, it would be coming out like that. But if you took your north pole and you put it up here, it's going to be attracted to it. So that means that you'd have an arrow pointing in to the magnet. And then what do you suppose would happen over here? Well, it's going to be attracted and repelled, so it goes sideways. And so if we connect all of these lines up, we're going to get something that looks like this. So it's coming out of the North Pole and it's going into the South Pole. Well, that's exactly what's happening down here, that it's coming out of this, it's swinging around, and then it's going back in again. Okay, and then you'd have the same thing on this side over here, and then like that, and then like that. Well, notice it's the same picture as this one here. So that the magnetic field generated by a current carrying loop is the same as the magnetic field being generated by a magnet. So we'll find out later why that has to be true. Okay, and then another way of testing for the presence of magnetism is going to be with a compass. So that if you were to take a compass over here and set it next to it, the compass needle is going to point in the direction of the magnetic field. So that the north end of the compass needle is going to be pointing in this direction when it's over here. But if we were to put it up here, then it's going to be pointing this way. So you can test out the presence of a magnetic field with a compass. And then there's a third way that you could do it with iron filings. So you probably have done this in elementary school. Take a magnet, put a piece of paper over it, sprinkle iron filings on it, and then it will outline the magnetic field of it. So that would be yet another way of detecting the presence of a magnetic field. So the last illustration of a magnetic field is the Earth itself. So the magnetic field of the Earth, let's put it over here, let's say that this is the Earth, is going to be, now this, if we were to tilt the Earth 23 degrees, all right, so that this represents perpendicular to the plane of the solar system. The Earth is tilted at a 23-degree angle. Don't worry about that. I'm just telling you that it is. The Earth is tilted at a 23-degree angle. So this is the north spin axis of the Earth, and then this is the south spin axis of the Earth. The Earth's magnetic field is tilted with respect to this by about 5 degrees. So if I was to, now I'm greatly exaggerating this, but just so that you can see it, that's only a 5-degree angle right there. So the Earth's magnetic field is actually tilted with respect to the spin axis by about 5 degrees. Again, don't worry about it. What I want you to know is, what does the magnetic field look like? Well, it is going to look exactly like the magnetic field of the bar magnet. And so it's going to, again, be going into the Earth at the North Pole, and it's going to be coming out of the Earth at the magnetic South Pole. And now this is kind of unusual, because what does that would be if you had a south magnetic pole. But this is the north geographic pole. So that the Earth's magnetic South Pole is located at the North Pole, and then the Earth's magnetic North Pole is located at the South Pole. And so it's reversed, and that's the reason why the north end of a compass, which is a little magnet, a compass is a magnet, and so there's the North Pole of that little tiny magnet, and then here's the South Pole. And so the north end of the magnet needs to be pointing north, which is really south. Well, sorry about that, but it's true. So notice that we started off with a line of current-carrying wire, and we ended up by taking that and bending it into a circle with 3 different pictures. So we have the current-carrying loop, we have the magnet, and then we have the Earth. And all 3 of these have the identical magnetic field. So on the exam, make sure that you are able to draw any of those magnetic fields, which isn't so bad because there's really only 2. You got this one where it's a straight line, and then the others are all just things that are going around in circles, and it's producing a magnetic field that is going to look like that. Okay, another thing I wanted you to show you before we go on is look at this picture here and then compare that to the electric dipole. So the electric dipole is the one on the bottom, and it's over there to the left. This was the electric field of a single charge, but if you were to put underneath it a positive charge and then draw the electric field for it, you notice that this line here would connect to that line, and then this line over here would connect to this line. I obviously have too many lines on my board here, but if you look carefully, that picture over there for the electric dipole is the same as this picture here. So this is a magnetic dipole, and that's its field, and then over to the side there is the electric dipole, and they're the same. Kind of interesting. Okay, so here are some typical magnetic fields in Tesla. So if you want to look it up and find out what is the magnetic field of the sun, what's the magnetic field of the Earth in terms of Teslas, you can look it up on that chart there. All right, so let's take a break, and when we come back, we're going to compare capacitors with inductors.